بسم الله الرحمن الرحيم رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقه قولي رب زدني علما رب زدني علما رب زدني علما صدق الله العظيم. Hopefully students you will be fine and enjoying good health in your homes. Now today we are starting a new chapter which consists on line, surface, and volume integrals and related integral theorems. This chapter uh, is very important not only for paper point of view but also in higher mathematics. Students, first of all, we start with an introduction. So far, we have dealt with derivative operations on vector field. In this chapter, we shall define the line integral, surface integral, and volume integral, and consider some important applications of these integrals. We shall see that a line integral is natural generalization of the definite integral. The surface integral is a generalization of a double integral. A volume integral is a generalization of triple integral of calculus. Students, you already studied in BSc calculus uh, that the first integral shows a line and second integral shows a surface and third integral shows a volume. And also, students, definite integral you already studied in the calculus is that those if the end limits of the integration are known, then we say this integral is a definite integral, otherwise not definite. So students, in line integral is a generalization of definite integral, and surface integral is a generalization of the double integral, and volume integral is a generalization of triple integral. Also, students, now which thing we study in this lecture, in this course, is that how line integral can be converted into double integral, and how the double integral is converted into triple integral. This thing makes a very important role in your application problems. Now, line integral can be transformed into double integral with the help of Green's theorem in the plane. Students, in plane, line integral can be transformed into double integral with the help of Green's theorem. What is the application of Green's theorem? Inshallah, we will study in next lecture Green's theorem. Green's theorem plays a very important role and convert first integral, mean line integral, into double integral and in plane. But Stokes' theorem, the line integral can be transformed into surface integral, and conversely, Stokes' theorem, students, convert line integral into surface integral, mean double integral, and conversely. But in space, not mentioned here, Stokes' theorem, where working, students, in space, but Green's theorem working in plane. Green's theorem is a special case of the Stokes theorem. We discuss in detail in upcoming lectures Stokes theorem and Green's theorem. Now, surface integral can be transformed into triple integral and conversely with the help of Gauss divergence theorem. Students, also an important thing. Surface integral can be transformed into triple integral. Surface integral can be transformed into triple integral. Mean we transform surface integral mean double integral. We transform double integral into triple integral with the help of Gauss divergence theorem. These transformations are of great practical importance. The corresponding theorems of Green's, Stokes, and Gauss serve as powerful tools in many practical as well as theoretical problems. Students, uh, these three theorems makes a very important role in practical problems. Inshallah, you will study in the upcoming lecture the practical problem how we use Gauss divergence theorem, how we convert, how we use Green's theorem, Stokes theorem, Gauss theorems in practical problems. Students, you uh, be kept in mind three things. First of all, when we discuss line integral, then uh, in behind of the mind makes one thing mean first integral. First integral. Okay. When we discuss the surface, then students in the behind of the mind we use double integral. And when we say working when we're working about the volume, then students the integral that will be used in the problem of volume is the triple integral. Okay. Now we are going to start first thing, which is line integral. First of all, before starting this, first topic is tangential line integral. Students, tangential line integral. Let a x y z, which is equal to a1 I plus a2 j plus a3 k, be a vector point function. Students, you know this terminology meaning vector point function. I explained this vector point function in the previous lecture, which is defined and continuous along the arc AB of the space curve C. Students, this vector A, vector point function, is defined continuously along the arc AB. Students, this point is A and this point is B. We'll let arc and say the name of C. Subdivide the arc AB into n segments by means of points P1, P2 up to so on Pn minus 1. Now students, subdivide A to B segment, which I say the name of arc, that is C. Divide into subparts, mean P naught, P naught, P1, P2, up to so on P3, P4, P5, and say Pk minus 1, Qk, Pk minus 1, and Pk. Okay, I minus K minus 1, then previous point stretch, and if we add plus 1 and then minus and plus 1 cancel out and pk generate, and in the last pn minus 1 and then pn. Students, we subdivide the arc AB into n segment by means of points P1, P2 up to so on Pn minus 1, chosen arbitrarily, and write A is equal to P naught. Students, I say here P naught which is equal to A, and B which is equal to Pn as shown in the figure 5.5. Consider one such segment Pk minus 1 Pk. Students, here I consider this one segment, that is Pk. Okay, it is Pk and Pk minus 1, and let the arc length of this segment, the arc length of this segment is delta sk. Students, one thing also, uh, in the previous uh, BSc calculus or in mathematical method, students, when we prove anything in mathematics, we use uh, the theorems or any mathematical tools not only in the whole surface, okay, but apply on one element. Like this, here we have this curve C, and we not apply the mathematical tools in whole curve, but first of all we starting with one segment. We take one segment and start working on this segment. If our working on this segment are okay, are to be whole, then we also apply similar working on this arc C, which is known as AB. Consider one such segment pk minus 1 pk, and let the arc length of this segment be delta sk. That is, k is equal to 1, 2 up to n. Let qk, that is xk, comma yk and comma zk, be any point on this segment pk minus 1 to pk. Students, here we are taking one point between this segment pk minus 1 to pk, and this segment is one taking up one point, that is qk, and we take a tangent on qk which is equal to, I say this vector is a. Let qk be any point on this segment and define a which is equal to ak. Students, this point qk, I take a tangent on this qk point and say this is a vector. Let tk be unit tangent vector on c at qk, and this vector and its unit vector is tk. The unit vector of this vector is tk. Students, tk. Similarly, like we studied in the previous, vector A and its component A1 and its unit vector, first component is I, second component A2 J component, and third component K unit vector. Here we use in general A vector and its unit tangent vector, that is T x T sorry T K unit vector. This is a K, okay, and K right in the subscript of T. Let Tk be unit tangent vector to C at Qk. We multiply the tangential component of A and OQ. We multiply the tangential component of A at OK with the arc length delta Sk of the corresponding segment Pk minus 1 Pk and form the sum. Students, you also know uh, in BSc Calculus, chapter number 5, first topic, uh, definite integral. Uh, the chapter name is definite integral. In we start when we start a first topic of definite integral of BSc Calculus. First topic is that we are starting the proof of definite integral. In this theorem, we work uh, to make the integral before similar working like this. And we work, when we work uh, to obtain the total length of this arc, we subdivided these arc C and add these one by one length of the arc. First of all, we add this length for second P1 to P2, third P2 to P3, fourth P4 to P5, and so on. Pn minus 1 to Pn. Here we use a general case Pk minus 1 to Pk. So sum this Ak, this is a vector, multiply to Tk and this arc length element delta Sk and summation K1 to n. If students you worry about this relation, uh, you open your BSc Calculus and see the chapter number 5 and first topic of chapter number 5, and you understand easily in chapter number 5 how we obtain this summation from partition. Okay, and after that we obtain this summation to integral. Only write in summation. First one is vector A, which is uh, say AK, and arc length multiply by its tangent unit vector. Tangent vector. Okay, tangent vector multiply its vector AK, also the arc length. Three things we multiply to obtain the integral. First one is we multiply a vector and its unit vector tangent vector with arc length delta sk. Okay, and then sum k1 to n. Mean if we apply k1 1 1, then we have this point p1. If we add uh, 2 2 2, then we obtain this p2 up to so on pn, and we add these one by one arc, these one by one this arc length, up to that this arc length, and then obtain the integral in the next. Let's see. Now take the limit of the sum as n goes to infinity in such a way that the arc length of each segment delta sk goes to 0. This limit of, if it exists, if this limit is exists, is called the tangential line integral of A. This is the tangential line integral. This is the tangential line integral of A. along the curve C from A to B is denoted as, along the curve C from A to B, okay, is denoted as A to B A dot TDS, or another way we write AB instead of C, A dot T, which is the unit tangent vector ds. How we obtained this relation, that is in detail I write limit n goes to infinity. When we apply the limit on this, when we apply the limit on this n goes to infinity. Similarly, see this, when we apply the limit on this, then we obtain a to b a ak denoted as a, we write a dot, and the tk is general t, and d delta sk is ds. Students, this thing is applied on this portion pk minus 1 to pk, and integral shows the total sum a to b, mean P naught to P1, P1 to P2, and P2 to up to zone P3, up to zone Pn minus 1 to Pn. Integral cover the whole sum a to b a dot t and ds. Here is we specify one portion. Now in this relation we generalize this relation. Ak converts into a, tk converts into t, and delta sk converts into ds. Since students t, that is unit tangential unit vector, is equal to dr over ds. This is the formula, t is equal to dr over ds, and r is the position vector of any point on C. Students, in the previous you study what is r. Small r mostly shows the position vector, and position vector is the distance or displacement from origin to any, to origin to point. But here r shows the position vector of any point on C. Okay, uh, any point p naught we consider, p1 we consider, p2 we consider, pk minus 1 we consider, so on. And it is usually to put, students, we cross multiply t head ds, which is equal to dr, and thus the line integral converts a to b a dot t unit vector ds, which is equal to, students, instead of this t unit vector ds, we can write dr, okay, dr. And also we ignore a to b in general, we write c, because ab is, another name is curve c a dot dr, and which is equal to, in specifically we write a as three component, a1 a2 and a3. Students, the value of a is a1i plus a2j plus a3k, and but dr r, which is equal to xi plus yj plus zk, and when we multiply dr d on this r, this is a vector, then makes dxi plus dyj plus dzk. Students, this relation and this relation, okay, we apply the dot product a dot dr, then a1 into dx, okay, plus a2 into dy, okay, and a3 into dz, okay, and I dot I is equal to 1, j dot j is equal to 1, and k dot k is equal to 1. This, where dr is this dr is called the differential displacement vector. Students, this dr is known as differential displacement vector. Okay. Now, students, the line integral a dot dr is this line integral a dot dr is sometimes called the scalar line integral of a vector field A. This is a scalar line vector of scalar line integral of a vector A. If C is closed curve, students, if we say, I say, okay, this is C is closed curve, we shall suppose simple closed curve. The line integral and around C is often denoted by this. This circle, students, shows the this circle shows the closed. Uh, this circle C shows this circle shows on integral shows uh, the closed integral mean a closed curve. Okay, mean uh, here from point A to B, this is a closed curve, and if I continue this curve C and up to so on is the curve C, then this curve is not closed. But if I study on A to B, then we say this is a closed curve and denoted as circle on the integral a dot dr, and write similarly a1 dx plus a2 dy and plus a3 dz. Okay, write simply closed circle on this integral and in this integral. If A is the force F on a particle moving along C, thus this line integral represents the work done by a force. Students, if A is a force F, if this vector I represent A, if this is a force vector, force, if this vector represent a force, if this vector is represent a force on a particle moving along C. Okay, a particle is moving. First of all, I say this is a particle. Uh, this particle, which is this particle, is moving along C, and when particle is on this point, then we I apply a force on this point to pull outward. Okay, if A is the force F on the particle moving along C, this line integral represents the work done by a force. In fluid mechanics, this integral is called the circulation of the A around C. Students, in third and fourth semester, uh, you study the course fluid mechanics, and this in fluid mechanics, the integral, this integral is called the circulation of A around C, where A represents the velocity of a fluid. In general, any integral which is to be evaluated along the curve is called line integral. Okay. Other form of the line integral is if integration phi and dr, then students phi uh, already you studied the meaning of phi. Phi is a scalar point function, and this function is uh, mean shows phi of x comma y comma z. Okay, and dr you already study in above that dr is a displacement vector. So apply this dr, which its value is dr value is equal to dxi plus dyj plus dzk, and apply this on this. So we obtained I integration phi dx plus j phi integration dy plus k integration phi dz. Okay. And if in a problem we take a cross multiplication of the displacement vector and vector A, then our result makes in this form: a1 I plus a2 j plus a3 k cross dxi plus dyj plus dzk. Students, here when we open this cross multiplication, then result makes in that form. Okay. Thus, the integral that involves differential displacement vector dr are called line integral. Thus, the integral that involves differential displacement vector dr are called line integral. Next, the general properties of line integral. These properties are very important in problem solving point of view. The following the properties of the line integral that are useful in computation and applications. Students, when we multiply k, which is any real constant, on line integral, then we take in the start of the integral, because k is a constant, and apply a dot dr on an integral. Second is when uh, we have two vectors a plus b, then and into dr, then we separate these a dot dr plus b dot dr. And similarly, when we have curve C in two parts, mean A to this point is C1 and this point to B is C2 curve, then we also take a partition A dot dr total, which is C, total is total curve is C. And first of all we find from point A to this point, integration A dot dr C1 plus, next is A dot dr, which is this point to this point, which is C2, where path C is subdivided into two are C1 and C2 that have the same orientation as C shown in the figure. If the sense of the orientation along C is resolved, the value of integral is multiplied by C1. Mean if we uh, take the direction changing, C2 down and C1 is up, then it's multiplied by -1. Students, simply uh, what is the meaning of integration, uh, yeah, or in the practical application or graphically representation of the integration is, you say only one thing is that integration first integral shows first integral the simple length of the arc. Okay. If C is piecewise smooth, consisting of smooth curves C1, C2 up to Cn as shown in the figure, the line integral A over C is defined as the sum of line integral of A over each of the smooth curve making up C. Since if like this, C1 this curve, and then C2 this curve, and C3 this curve, and C4 this curve, and so on to n curves. Then we add one by one these curves, and result is equal to A dot dr. In this sum, the orientation along C must be maintained over the curve C1, C2 up to Cn. That is the initial point of Cj is the terminal point of Cj minus 1. This requirement is indicated by the arrows as shown in the figure. Next is example number 1. In this example, we apply these. general properties to solve the problem. Inshallah, students, in the next lecture, we solve this example and other examples. Students, if you have any problem in this lecture, write in comment box. Allah Hafiz.